To understand phototransduction, we must start with panel A. In the left of the diagram, the photoreceptor is shown in complete darkness. Even though no light is present, the cell is still active. At the top of the image, in the outer segment, the retinal is shown in the 11-cis configuration. This means no photons have been absorbed yet and the photopigment is inactive. Inside the cell, you can see several hexagon-shaped molecules called cGMP, a crucial messenger molecule. In darkness, cGMP levels are high. These molecules bind to sodium ion channels in the outer segment membrane channels. This steady influx of positive charge is called the dark current. As a result of the dark current, the membrane potential of the photoreceptor remains relatively depolarized, meaning that the cell's interior becomes less negative or more positive than its resting state. This is shown in the small graph at the bottom of panel A. At the bottom of the cell, near the synaptic terminal, this depolarized state causes continuous release of neurotransmitters, labeled as GLU or glutamate in the diagram. The photoreceptor is actively signaling to downstream neurons that no light is present. Because the cell is already active in the dark, light does not need to turn the cell on. Instead, light interrupts the steady activity. This allows the visual system to encode information as changes away from the dark baseline, which makes it faster and more sensitive. Now that we understand photoreceptors in the dark, we can see how light changes this. In panel B, the same photoreceptor is shown after light has been absorbed. The key difference here is that the steady activity in the dark has been interrupted. At the top of the diagram, a photon strikes the retinal, causing it to change shape from the cis form to the trans form. This change activates the rhodopsin. Activated rhodopsin then activates a signaling protein called transducin, which in turn activates the enzyme PDE. PDE rapidly breaks down cGMP, the molecule that keeps sodium channels open in the dark. As cGMP levels drop, the sodium channels close, which is shown clearly in the diagram by the blocked channels. With fewer sodium ions entering the cell, the dark current is reduced. The membrane potential shifts toward a more negative value, a change known as hyperpolarization. At the synaptic terminal, this hyperpolarization reduces neurotransmitter release. The photoreceptor is now signaling that light is present.